Hmm. Hello, everyone. Just waiting for a couple more people to join up. Está lloviendo mañana. Esta mañana. Okay. I am at about 20 viewers, so I'm going to go ahead and start. Um, so let me just review last time. And before I review, I want to ask this question. So this is kind of a challenge question, if you will. I'm going to call it a challenge question. It's not really that tough, but um, let's suppose a particle undergoes SHM with amplitude A. Um, what is the distance traveled by the particle um, during one period, one full period? So if you think you know the answer to that, um, so kind of while I'm reviewing what we did last time, if you think you know the answer to that, go ahead and type it into the chat. Okay. And I'll leave some space here so I can put the explanation. Okay, so what we did last time was we studied energy and the mass spring system. And so basically what we found was that, well, hello, Hazel. Hazel's funny because when she closes her mouth, her lips get curled up underneath. And so she kind of does this like weird thing where she closes her mouth and it's all like curled and up. It's funny. So what we learned about is that no one's going to type into the chat for this. My challenge question. So what we learned is that basically, ooh, nice. 4A is the correct answer. Okay. So why is that? Well, if you think about it, here's the equilibrium point. Here's plus A. And here is minus A. So if you do a full period, you go across and you come back to where you started. So you go a distance A, a distance A, a distance A, and a distance A. So that's a total of 4A. Very nice. So, simple harmonic motion in the case of a mass spring system is an exchange between elastic potential energy and kinetic energy. So the total energy of the motion is 1/2 kx squared plus 1/2 mv squared. So kinetic energy plus potential energy. All right. Now, we could take this this energy and we could evaluate it anywhere in the motion of the particle, and we get the same number, and that's because energy is conserved. So if we choose to evaluate the energy at the extreme point, the particle has no speed, because if it did have speed, it would still be moving further than 1 amplitude away. Okay? So we could evaluate the energy at the extreme point, in which case we have no kinetic energy and all potential energy. And at that location, the energy is expressed as 1/2 Ka squared. So this is at the extreme point. Okay. Or we could evaluate it as it passes through equilibrium. If we evaluate the energy as it passes through equilibrium, well, equilibrium is defined by x equals 0, so there is no potential energy, so we have all kinetic energy. Now, because we have all kinetic energy, the particle has reached its maximum speed. So if we evaluate the energy at the extreme point, we get 1/2 m v max, at the equilibrium point, we get 1/2 m v max squared. So this is the energy while passing through equilibrium. Okay? And then this is, of course, the energy at any general point. So, excuse me. So we can set any two of these equal to each other, and we can use that to solve problems. And that's exactly what we're going to do today. So today we're just going to play around with these equations and get some results. So probably this front page is going to be just the formulas that I want you to have, and then the back page we'll do some examples. So the first equation that we can get is I'm going to set these two equal to each other. So I'm going to have 1/2 kx squared plus 1/2 mv squared equals 1/2 Ka squared. All right. So now what I'm going to do is I'm going to notice that if I do that, every single term has 1/2, so I can cancel out 1/2. Okay. And then what I'm going to do is subtract this term to the other side. So I have mv squared equals Ka squared minus Kx squared. And then I'm going to factor out a K here. So I have K times the quantity A squared minus X squared equals mv squared. Okay, and then I'm going to divide both sides by m. So I have v squared equals k over m times the quantity a squared minus x squared And then I take the square root, and I get v equals square root of k over m times square root of a squared minus x squared. Okay, so this is the first equation that I want you to have for today's lesson. And so basically what this equation does is it has speed as a function of position. Okay? Speed as a function of position. So that's a nice equation. If we were to graph this equation, so if we were to graph speed as a function of position, it looks like this. So basically, if x equals 0, we are at our maximum speed. Okay. If x equals the amplitude, then remember, when you're at the extreme point, when your x value is equal to 1 amplitude away from the equilibrium point, your speed is 0. Okay? And the reason is that if your speed wasn't 0, you would keep on going past equilibrium. So this is a point. And then, so this is basically the equation of an ellipse. So it kind of curves down like this. It goes like this. So that the further you get from equilibrium, the smaller your speed gets until you reach the amplitude where your speed is 0. Okay? So that's what this equation is saying. So that's a really useful equation. Okay? We can get another equation by setting these two equal to each other. So we could say 1/2 Ka squared equals 1/2 mv squared, mv max squared. So this is setting the energy at the extreme point equal to the energy at the equilibrium point. Again, the 1/2s cancel out. And I can divide both sides by m. So I have k over m times a squared equals v max squared. Take the square root of both sides. I get square root of k over m times the amplitude equals v max. So this is giving the maximum speed as a function of the amplitude. Okay. So that's a pretty useful equation. What this equation is saying is the bigger the amplitude is, so the more you pull the mass back before you let it go and start undergoing simple harmonic motion, the bigger the speed it's going to have once it passes through equilibrium. Okay? So that's a pretty useful equation. And a third equation that is nice to know, and this equation is just comes from Newton's second law. So if we start out with net force equals ma, where little a is the acceleration, remember, the net force is the elastic force when you're undergoing simple harmonic motion. Okay. And so that equals ma minus kx, elastic force equals ma. And so then I can divide both sides by m, so I get minus k over m times x equals a. Now, what if I wanted to figure out what is the maximum acceleration? Okay, at what location is the acceleration the maximum? So what we can see here is that this is a linear relationship, okay? And so if we want to make the acceleration as big as possible, we should make x as small as possible, as negative as possible, okay? So that's because there's a negative sign here. So to make acceleration big, we have to make position very negative. Now, as we know from simple harmonic motion goes between plus an amplitude and minus an amplitude. So the most negative value that x can take is at negative a. All right? So if I plug in negative a for the position, what I get, the negatives cancel out, and I get k over m times the amplitude is the maximum acceleration. So you can figure out what the biggest acceleration is. All right? So these are pretty much three equations that are really useful for simple harmonic motion. Okay. And you could get one other equation by setting the energy at a general point equal to the energy while passing through equilibrium. I'm not going to solve the equation, but that would be, you can also say this, and this equation is true. So this equation is also useful. Okay. So let's go ahead and do some examples using this. So we have let's suppose we have a 2 kilogram mass is connected to a spring of stiffness, let's say 150 newtons per meter. The mass is pulled, let's say 0.3 meters from equilibrium and released from rest. Okay, so let's just go through this these two sentences and get our information that we're going to need to solve the problem. So the first piece of information we're going to need is right here. This is M. Okay. The second piece of information, it's a spring of stiffness 150 newtons per meter. So that is K. And then the mass is pulled 0.3 meters from equilibrium and released from rest. So what that means is that 0.3 meters from equilibrium is the farthest it's going to get from equilibrium because it doesn't have any velocity at that location, so it's never going to go any further away. So that means that this is the amplitude. Okay? So we can just go through and we can just start answering questions about it, about this motion. So for example, what if I said, what is the period? The period is going to be 2 pi square root of m over k. So that's 2 pi square root of 2 over 150. And that is 0.73 seconds. So that is the period. I could say Could ask the question like, what is the max speed? Vmax is square root of k over m times the amplitude. So that's going to be square root of 150 over 2 times the amplitude, which is 0.3. So we're going to get 2.6 meters per second is the max speed. We could calculate the maximum acceleration. The maximum acceleration is going to be k over m times the amplitude. Once again, I don't want to confuse anyone. Lowercase a is acceleration, uppercase a is amplitude, so those are two completely different quantities. So we have that the stiffness is 150, the mass is 2, the amplitude is 0.3. So that's going to give us 75 times 0.3. So the maximum acceleration is 22.5 meters per second squared. Let me box these in. So this is all fairly straightforward, okay? The nice thing about simple harmonic motion is it's more or less just using the equations, okay? And then we also could have questions. These are probably the most difficult questions. If I ask something like, what is the speed when 0.4 meters from equilibrium? Now, I'm not going to answer that yet, okay? I want you to type it into the chat if you know the answer to this question. It does not require any math whatsoever, all right? So type in the answer to that if you know it. And while I wait for an answer, I'm going to put in the last part, which is, what is the speed when 0.2 meters from equilibrium? Okay, so whenever we're trying to find the speed at a certain location, we want to use this equation, v equals square root of k over m times square root of a squared minus x squared. So square root of k over m is going to be square root of 150 over 2. Square root of amplitude, the amplitude is 0.3. And the position at which we want to know what the speed is 0.2. So we have minus 0.2 squared. So you're squaring each of these individually and subtracting them. So just be aware of that. And so for this, we get 1.94 meters per second. So this makes a lot of sense, right? Just as a sanity check, your speed when you are 0.2 meters from equilibrium should absolutely be less than your maximum speed, right? So 1.94 is in fact less than 2.6, okay, meters per second. So we're less than the max speed. So there's excellent. So in the chat, the correct answer for D is there. So if the amplitude is 0.3 meters, then that means you are never going to get more than 0.3 meters from equilibrium. So when to ask a question like, what is the speed when you are 0.4 meters from equilibrium, it doesn't make sense. So I would say does not exist or doesn't get there, something like that. It's kind of interesting to see what happens in the equation when you plug in 0.4. So if you did that, you would get v equals square root of 150 over 2 times square root of 0.3 squared minus 0.4 squared. So when you do that, if you do 0.3 squared minus 0.4 squared, you get a number that is less than 0. So you end up taking the square root of a negative number, and you would get an imaginary velocity, which isn't possible. The velocity is a real number. Okay, so that's how. So you can answer this question both in terms of just intuition and saying it's never going to get that far from equilibrium, or you could try and work out the math and you get an imaginary number for your velocity. Okay. I'm going to do one that is a little bit more complicated, okay, just to kind of show you how this can work. So what if we had a mass spring system, okay, and here's the mass. This is and it's sitting, the mass is sitting at x equals 0. Okay. Let's suppose that the stiffness is 100 newtons per meter. And let's suppose that this is a 2 kilogram mass. All right. So if we just have a mass that is sitting at equilibrium with no velocity, it's just going to stay at equilibrium. Okay. But what if we sent a 1 kilogram mass towards it? Okay. It's a 1 kilogram mass, and it's headed this way at let's say 30 meters per second. And let's say that these two masses collide and they have a completely inelastic collision. Okay. And now we want to describe it. So this is kind of interesting. So basically one mass hits the other mass, they stick together, boing, and then they start vibrating back and forth. Okay, so it's like this. All right. So let's just answer some questions here. So what would be the period of the motion? Well, the period would be 2 pi square root of m over k. But if we think about it, these two are stuck together. So the amount of mass vibrating, even though I'm kind of trying to trick you with putting a 2 kilogram mass here, the amount of mass vibrating once they stick together is both of them. So it's going to be 2 plus 1. So it's going to be 2 pi square root of 3 over 100. That many seconds. I don't really care what the answer is. It's just for demonstration purposes. I could ask, what is the maximum speed? All right. And so to answer this question, we have to actually use momentum. All right. Because basically what's going to happen is that the 1 kilogram mass is going to come in, smack into the 2 kilogram mass, and then they're both going to start moving to the left. And as they start moving to the left, they're going to compress the spring. And in the process of compressing the spring, that's going to slow the masses down. So basically what we want is we want the speed just after collision. Okay, so I'm going to use P initial equals P final. So the initial momentum is 1 kilogram traveling with a velocity of 30 meters per second. Technically, it's negative 30, but you know, imagine I flipped it the other way. I'm just trying to get the speed. And then afterwards, we have 3 kilograms moving. Okay. And then this will be the velocity after the collision. So I can see that the velocity after the collision is 10 meters per second. So this is going to be Vmax. Okay. So then we could ask a question like, what is the amplitude? Well, if I wanted to know what is the amplitude of the resulting simple harmonic motion, then you would have that equation that Vmax equals square root of k over m times the amplitude. So I know that Vmax is 10. I know that the stiffness of the spring is 100. And I know that the amount of mass moving is 3 kilograms. So I could take this equation and I could solve for the amplitude. All right. And then I could ask questions like, well, what is its speed at a certain location, et cetera, et cetera. So I just kind of wanted to show you a little bit more advanced problem involving the mass spring system, where we're bringing in other topics from physics. So we're not just staying in the realm of mass spring system, we're also bringing in momentum into the game. Okay, so that's really what happens when you have more high-level physics, is you start bringing in multiple concepts simultaneously and bringing them together to solve a problem. Okay. Just really briefly, so I'm almost done here, I wanted to talk about energy and the simple pendulum. Okay. Energy and the simple pendulum. So if we think about a simple pendulum, all right, here's the ceiling, and we have the pendulum bob. Okay, and the pendulum, because the string is of a fixed length, the pendulum is going to go in this kind of like circular arc. Okay. So if we imagine the pendulum when it's right here, all right, it has a certain amount of gravitational. So if we called this y equals 0, we can see that as the pendulum is swinging, because it has to go in this circular arc, it's actually gaining elevation as it swings. Okay, so it's gaining gravitational potential energy and losing kinetic energy. Okay, so the point I was trying to get at is that for the simple pendulum, we have the simple pendulum is an exchange between kinetic energy and gravitational potential energy back and forth. So whereas the mass spring system was an exchange between kinetic energy and elastic potential energy back and forth, the simple pendulum is an exchange between kinetic energy and gravitational potential energy back and forth. So we have gravitational potential energy at the extreme point, and then we have our maximum kinetic energy at the equilibrium point, which is when the pendulum is up and down. Okay? So our energy equation is going to be not 1/2 kx squared plus 1/2 mv squared. It's going to be mgy plus 1/2 mv squared. Okay? And so this is the energy at a general point. All right. But if we were at the extreme point, we have all gravitational potential energy. So if I wanted to evaluate it at the extreme point, I would have mg, the maximum elevation. So this is evaluating it at the extreme point. Okay. Or I could evaluate it as it's passing through equilibrium, where it's going to have maximum kinetic energy. So we have 1/2 mv max squared. So this is evaluating the energy at while passing through equilibrium. All right. So the ideas are exactly the same. The form that the potential energy takes is a different form, but it's the exact same idea: mass spring system versus simple pendulum. All right, class. That is my lesson for today. I hope it made